Hey guys, this video is a quick video over bond enthalpy. Alright, so bond enthalpy is the heat required to break a bond. So you have to put heat in to break them, and so that's going to be endothermic, which means it's always going to be positive. The opposite of breaking a bond is making a bond, and so those values are always going to be exothermic, and so they're going to be negative. And you can remember that with, if you have a pencil and you want to break that pencil, you're going to have to put energy in to break it. If the pencil is smaller, you're going to have to put more energy in. And if it's even smaller, it's almost impossible to break with using just your hands. So if you're going to break something, you have to put energy in. If you're going to make something, you're going to get energy out of it. All right? If we were to compare the C to H and the C to C bonds, we could see here that C to H is a stronger bond, so it's probably shorter. And the reason that it's shorter is because hydrogen's smaller, so it can get closer to carbon. And carbon-carbon bond is going to be a little bit longer. All right, so the two nuclei between carbon and carbon have to be slightly further apart to get that perfect energy so that it can form a good bond. While carbon-hydrogen, the nuclei get slightly closer because of the way that the orbitals have to overlap in order to make the bond work. All right, and if we go down here and we look at the multiple bonds, a C to C double bond is 614, while C to C triple bond is 839. So that just means that the C to C triple bond is stronger. Duh, it's an extra bond, but it's also much shorter. All right, and so if you look at HF versus HH, well, HF is a very polar bond. It forms a hydrogen bond between the molecules of HF, but not only that, it's going to be a shorter, stronger bond because of the polarity of it. A lot of the time, polar bonds are much stronger. All right, so if we have reactants going to products, then these bonds have to break, and these bonds are going to be made. And so since the bond enthalpies that are given to you are all positive values, that means that these are breaking. So there is a formula if you're looking for delta H of a reaction, and you can get it by using the bond enthalpies of reactants minus the bond enthalpies of products. And this goes against everything we've ever learned about delta H or delta S or delta G. We usually do products minus reactants. But because we have to change the signs of these over here in the table to negative, that's why we do reactants minus products. So you can either remember this equation, or you can remember that you're going to have to change the signs of these and then add them to the amount of heat that you're going to have to put in to break the bonds of the reactant. So let's do an example and then this will be finished. All right, so we want to do the reaction of nitrogen plus hydrogen goes to ammonia. So if I have nitrogen, it's nitrogen plus 3 hydrogen goes to 2 NH3. And nitrogen is going to be triple bonded. And then we have 3 hydrogens. And NH3 looks like that, and there's 2 of them. The first one is the nitrogen-nitrogen triple bond, which is right here, and it's 941 kilojoules per mole. And then we have 3 hydrogen, so there'll be 3 of these bonds right there. Hydrogen is right here, so that's 436. And then for ammonia, N to H bond is right here, and it's 391. And we have 3 of them in the molecule, 1, 2, 3. And that's times 2, so that's actually 6. So this has to change to negative over here, and then this will be our reactants. So if we perform that calculation, we get that the delta H of this reaction will be equal to negative 97 kilojoules per mole of reaction. So that means for this reaction to happen the way that it's written, we get a delta H equal to negative 97 kilojoules per mole. Now, if we wanted it per mole of ammonia produced, so per mole of this, it would actually be half of that because this is for 2 of these.